criterion. So for this, so let's just consider this. So if we consider this space of volume 1 Hermitian metrics, we need to consider the identity map. This is kind of the nicest base point for Lie theory. I guess the, all right, so then the tangent space, I'll just put the identity map here like this. This is going to be equal to okay. So this is going to be all the Hermitian symmetric matrices with trace zero. So the trace zero is just kind of the determinant condition. When you differentiate the special linear condition, determinant equals 1, you get trace zero. Okay, so that's kind of useful to assume for some technical reasons, which we'll see. And so for this, we have the following that. So let's say f from n to m with f of x goes to the identity. Then we have the following Higgs field given by df 1, 0 is phi in h0 of n. So n is going to be sigma, the Riemann surface. Okay, so this is going to be the following criterion here. So I guess one thing to note is that this is the df, so this is going to be the map F, of course. So the complexification of this is the following. So this is just going to be all the trace-free endomorphisms. Okay, so this is how we get kind of to the endomorphism here, and moreover we have, and so kind of the criterion for the map to be harmonic is that phi is holomorphic. So I misstated something last time, I believe, which Subhajoy pointed out. So if M is a surface, then this another criterion is that the pullback of the metric to 0 part is holomorphic. But I don't believe this is true in general. So that's so this is kind of the criterion. Although this part, this is this Hopf differential. So So I believe that this may not be true in general. Is that?
Did you mean that n is a surface?
If M is also a surface.
Oh, m is also a surface.
Yeah. So I believe I misstated kind of the criterion there. But you can see in this situation, we will have kind of a holomorphic Hopf differential. It's just not kind of an equivalence, an equivalent criterion in general, I believe. Okay, so so in this case we do have alpha is going to be trace of phi squared. And this is a way of, and so this makes sense because of the endomorphism structure here, by the endomorphism structure here. And so this is really kind of follows from the fact that M is a symmetric space. Okay. Since M is this sort of symmetric space, then we can find we have kind of this extra structure to give this extra structure on the Higgs field to kind of have this nice relationship. Okay. All right. So that's a little bit of recall. A little bit of a recap. Another thing that I should mention that was kind of related to last time is that so you recall kind of harmonic maps are the critical points of the energy functional. So kind of the integral over n. So this depends on kind of G and H d vol G, okay? And so this is, and so harmonic maps need not be immersions. So, so in particular, it is also useful to, but when we were having our discussion of minimal surfaces, we started with the assumption that it's an immersion, because we want to be able to pull back the metric and do all kind of these computations with the second fundamental form and the, yeah, and all sorts of things like that. So kind of our computations depend on the, in order to compute kind of, say, the mean curvature vector, it depends on kind of the fact that it's an immersion for minimal surfaces. So if, so for surfaces, for minimal surfaces, and so this is strictly the case, dimension of n is equal to 2, then, and I believe you can say something else otherwise, we can also talk of branched minimal surfaces. Okay? And I'm not really going to define this kind of geometrically, but more analytically. And so what happens in this case is that these will be kind of harmonic maps. These will be conformal harmonic maps, so which are not constant. Okay. So, so you recall kind of a conformal harmonic map. So the conformal condition is that, say, this alpha is equal to 0, and the harmonic map condition is that this phi is holomorphic. And so these two conditions don't necessarily imply that the image is an immersion, that the map is an immersion. But everything is analytic in the background. And so if it's not constant, then you only have kind of it only fails to be an immersion at isolated points. So may fail to be an immersion at isolated points. Okay? So this is kind of, so to save kind of this branched minimal surface, I'm just going to restrict to the dimension 2 case because, I mean, in higher dimensions, I think you could say something, but it's going to be much messier because, I mean, the holomorphic data is not there. All right? Okay, so those are a few remarks. And let me talk about kind of the main first topic of today would be at least part of, so I'm not going to talk about the entire thing, the nonlinear Hodge correspondence. And so this is due to, so Hitchin and Simpson. So Hitchin introduced Higgs, the theory of Higgs bundles on Riemann surfaces, and Simpson proved kind of expanded this theory to a lot of other interesting cases. And then there's kind of some some proofs in the opposite direction of Corlett and Donaldson. Okay, so we're going to consider mainly Hitchin and Simpson's theory first. So let's consider sigma is going to be a compact Riemann surface, and let's assume that the genus, it's called the genus at least 2. So let E over sigma, so this be a holomorphic vector bundle. So either you can define this in terms of a del bar operator, which we discussed last time, or I guess a little bit more straightforward way, in terms of there's transition functions which are always holomorphic. Yeah. Okay. When you kind of pass from one coordinate chart on sigma to the next. Okay. So we're going to assume, so this is going to be for now, and for simplicity, that degree of E is equal to 0. This just makes kind of one of the criteria that we'll have to use a little bit simpler. And so phi is going to be a section. So H0 means holomorphic section, recall, of sigma. And then from this, we're going to have the canonical bundle tensor the endomorphisms of E. Okay? Okay. And so that's just, so in this case, we were just essentially working locally. And we just think about this, the bundle of E is just kind of some constant Cn. We're not, this is not going to work in general on a more complicated manifold. All right. So we're going to assume also, and so this I'll need to have that over sigma, this collection of E and phi is a stable Higgs bundle. And so I'll have to kind of talk about, so this is and in most situations, a generic condition, but so it's kind of, it's, in order to get kind of the existence theorem that we need, we will need to have this. And I'll talk about what this is later. Then, so I guess I'll mention this now. So if F is, so let's say this has rank n, is a non-trivial, so in other words, the rank of F is strictly between 0 and n, holomorphic subbundle of E, then the degree of F is negative. Okay. So there are various ways of defining the degree. One way is you could kind of consider, since this is just a Riemann surface, you could kind of consider the first Chern class and see if this integral over the Riemann surface is negative, or kind of the pairing over the appropriate homology class. All right. Okay. And so this, this degree F is negative. This is a rather simplified expression that depends on the degree of E being 0. If the degree of E is non-zero, you have to define something called slope stability, in which case there's an inequality involving the slope of F and the slope of E. All right. So then, there exists a Hermitian metric. I'll call it M, small m, on E, and this is going to be unique up to scaling, which I'll write as nabla sub m on E is satisfies the following. We're going to make a new connection out of the Chern connection, nabla m plus phi plus the dual of phi with respect to the, yeah. Oh, yeah, sorry about that, yes. Not even, yeah, okay, yes, of course, sorry about this. Yeah, I wrote that in my notes, let's say, yes, sorry about that. So, yes. Yes, okay, thanks. Yeah, so these are phi invariant, so this is kind of an older kind of version of stability. I guess this goes back to Narasimha and Seshadri without the phi condition. So if phi is equal to 0, then this condition is vacuous, okay? So kind of the upshot is that, so with this kind of, in general, non-trivial phi, then there are more chances for this, this bundle to be stable, the Higgs bundle to be stable. All right. F tensor K, sorry, yep. Yes. Okay, keep me on my toes, yeah, so, yes, okay. This okay now? All right, thanks. So then this is a flat connection on E. And so in other words, the curvature of nabla m plus a bracket, a phi, and its dual are equal to 0. Okay? So the curvature of this connection kind of breaks down into the curvature of this plus this bracket term. Okay? All right. And so again, this is one of those situations where if degree of E is non-zero, then we will not quite get a flat connection, but something called projectively flat, which we'll see in an example later. All right. Okay. So then as a consequence of these equations, so the M, we can think about this as we kind of pick a base point and a universal cover of sigma goes to SLNC over SUN is harmonic. And so if you pass to kind of a quotient, this is the situation where M is a harmonic section of a bundle, but kind of on the universal cover, it's just a map. The holonomy of nabla, so given by parallel transport, or maybe its inverse, gives a representation rho from pi 1 of sigma into SLNC, and M is rho equivariant in the sense that we have the following. So if you have gamma is a deck transformation, and M is this map, so I guess I'm calling this capital M, so let's call this capital M still. Little m. And so this is the induced map. So I'll just call this again rho of gamma. So this is the induced map of this representation on the quotient space. Yeah. Okay. So M is rho equivariant. So in other words, you can think about, so if you take kind of the quotient by this rho action, we have the following. So we have M divided by So this is going to be a bundle whose fiber is, with fiber yeah, so then we have kind of, actually, I think I wrote that down wrong. So let me not say that. So anyway, let's just say so you get a bundle. So we get a bundle over sigma. So let's say the bundle is something like this. And then the map so there's an induced map M to this bundle. And so this kind of goes into the fiber map. Okay. All right. So this is the setup. So, and I guess one more thing to say is that our restriction to the degree of E is equal to 0, this kind of allows us to consider more naturally SLNC maps as opposed to kind of GLNC, so, which also makes things a little bit nicer. All right. Okay. All right. So moreover, if you, and this is kind of part of, I mean, not kind of the main part, but part of kind of the Corlett-Donaldson part of the nonlinear Hodge correspondence, is that if you have such a setup with M and delta, et cetera, or nabla, et cetera, then we can recover E and phi, okay? And so this is kind of essentially kind of recovering phi from a harmonic map is essentially this discussion that we had last time, okay? And so you can do this, and also, and this is either stable or a product of stable. Bundles, which is polystable. Okay. So there are two cases.
I have a question from online.
Yes, yes.
If the Hitching equation which you wrote are nabla plus phi commutator phi star equals to 0, that is equivalent to sigma tilde being a minimal immersion. Is that correct, or am I understanding it wrong?
It's not a minimal immersion, it's a harmonic map. So
Just a harmonic map so far. Okay.
It's a harmonic map so far. So you would have to look further to this kind of
Conformality. Okay.
Minimal, right?
Okay. Thank you.
So if it's in addition conformal, so kind of this local map from the Riemann surface to the symmetric space, if that is conformal, then it, in addition to being harmonic, then it is minimal.
Okay. Thank you. Yeah.
All right. And so there are two, yes. So in terms of this, the polystable condition, so if the bundle is strictly polystable, then this means essentially that the flat connection is reducible, right? And so the irreducible case is the stable case. Okay. All right. So I should say Corlett-Donaldson's theorem is broader than this in that you don't. You really kind of start with kind of a unitary structure on a bundle and nabla, and then you construct M. So again, this is kind of a constructing this sort of harmonic map, but from a different point of view. Okay. All right. So Okay, so I guess one thing to note here is that, so let me say that in order for this theory, so maybe I'll erase this stuff. So having the symmetric space of non-compact type is essential for this nonlinear Hodge correspondence. And so, I guess, and so kind of one of the reasons for this is that in order to prove this, so the proof of Hitchin's original proof, I'll talk about mainly, this kind of involves solving kind of systems of, let's say, a second order system, elliptic system of say, semilinear system. So it's not even a system of PDEs. And so kind of in most cases, then the solution is not explicit in almost all cases. And so in particular, what you have to do is you need to rely on kind of some powerful existence techniques from the elliptic theory. So you need kind of the elliptic theory. And so maybe I'll just kind of mention the maximum principle and integration by parts, which I'm not going to explain the details of how this works, to get the proof to work. So when you apply these standard techniques of the elliptic theory, it's very important to have kind of in various terms to have the correct sign. So non-compact, so kind of the symmetric space of non-compact type, this corresponds to the good signs in the elliptic theory. And so this is kind of, so it's essential to have, to talk about these special sorts of symmetric spaces. There are other kind of symmetric spaces of compact type, such as kind of spheres and things like that. And you can kind of work out a similar theory that looks kind of formally the same, but when you get down to kind of trying to prove these kind of existence results, then there are not good signs there, and that kind of hinders, makes kind of the theory much more complicated. You don't get kind of such clean existence results. Okay. All right. Okay, so I guess one thing to note is that in this situation, you notice that this is not quite as straightforward. So for minimal surfaces in R3, you recall that you have kind of some, say for the Weierstrass representation, you have some holomorphic data, and then there are kind of some fairly simple formulas and integrals to parameterize the surface. And we also kind of see this, of course, for maximal surfaces in Lorentzian 3 space as well, as we saw yesterday. And so this is not quite as simple here, because when we have some holomorphic data, and we get kind of a very nice existence and uniqueness result in the nonlinear Hodge correspondence, but it goes through the system of PDEs, whose solutions are not explicit for us. Okay, so but that's kind of about as good as it gets. All right. Do you have any questions so far? Okay. So this stuff, I mean, I think I'm going to do, I mean, in some sense, just kind of the formal parts of before I kind of move on to other things, I want to do kind of one situation where you can see what how these various definitions work. And so this is due to kind of Hitchin's original paper on this. All right. Okay. So let sigma be genus greater than or equal to 2, compact Riemann surface. This is going to be kind of standard assumptions for sigma. And K is going to be the canonical bundle. So I guess we're going to have kind of a local frame of just dz. So this is a holomorphic line bundle. So what we're going to do is we're going to choose a bundle which I'll call k to the 1/2, so that k to the 1/2, this is going to be a line bundle, is equal to k. Okay, and so this is always possible, but involves a non-trivial choice. So basically, you're taking this thing, which is kind of quite well defined, and in order to construct the other bundle, you need to take some sort of square root, and there are some choices doing that, of course, in the complement. Okay. Okay. And so now what we're going to do is we're going to let E be a very special vector bundle, k to the 1/2 plus. So this is going to be a rank 2 vector bundle. And we're going to consider a Higgs field being given by the following. So this is going to be so Q is going to be a holomorphic quadratic differential. So k squared means that this is going to be locally like, so this is going to be essentially like our alpha before. So locally like a holomorphic function times dz squared. And so I guess the way that this, so phi is in the, okay, I'll write, or do I want to write this? I'll write it over here. So phi is, of course, a section of K tensor the endomorphisms of E. And so in this case, well, the endomorphisms of E are quite explicit. And when you write things down in terms of a matrix, you can take the first part into the first part. You can take and so forth. So in terms of bundles here, we have the following. So of these coefficients, so if you have this this sort of situation where phi is this endomorphism, then we have this, the bundles break down like this. So this will be kind of naturally the trivial bundle, the canonical bundle, and then quadratic differentials. Okay? All right. So then, in this case, the stability condition is something that's not so difficult to work out. Is that so E has rank 2, so we only need to consider line subbundles. And these are going to be only, since this is a product, a non-trivial product, these are the only line subbundles here. Okay? And so now what we can do is we can kind of check. So, so if phi is where Q is not identically 0, then neither k to the 1/2 or k to the minus 1/2 are phi invariant. But in the case, but if Q is identically 0, we have phi is, and so in this case, we get phi to the minus 1/2 is 0, which is contained in k to the minus 1/2. Okay? So if you kind of look at this, so basically the way this works is just in terms of matrix multiplication. So you have kind of a k to the 1/2 here, k to the minus 1/2 here. And so if you do the matrix multiplication, there's all these terms that have with the k to the minus 1/2 become 0 here. The top row is 0. Okay? And so this, but in this case, the degree of k to the minus 1/2 is minus 1/2 to the degree of k, which is standard by Riemann-Roch. So minus 1/2 times 2g minus 2 by the Riemann-Roch theorem, which is 1 minus g is negative if g is bigger than or equal to 2, which is what we assume. Okay? So this is a, so this setup does give us a, and I guess also I should check that kind of the degree of E itself, this is going to be, the degree of, is going to be 0. So it's just kind of a direct sum of a line bundle and its inverse. So they kind of add up to be 0. Okay? So this is how you can kind of check the stability in this case. So I should say, so let's see. This is a stable Higgs bundle over sigma. Okay? And so you notice again that this is, it's kind of an improvement. The Higgs bundle is an improvement because if phi, if you took this bundle and phi is identically 0, not just this term, but everything is 0, then the bundle would not be stable in kind of the more classical sense, right? Because in that case, phi of k to the 1/2 would also be 0, which would be contained in itself, but its degree is the negative of this, which is positive. So, so it's kind of, so the Higgs bundle theory is kind of a way to get, in some sense, if you're looking from vector bundle land, the Higgs bundle theory is a way to kind of get more examples of stability, because you put in an extra condition that has to be satisfied. Okay. Okay. All right. So this is, so in fact, we have kind of the metric M on E is of the form of the following. And so I think I'm going to have to start repeating some letters here because I'm kind of running out of space. So you can use kind of the symmetry of the Higgs field to show that this, and also the uniqueness to kind of show that these sorts of things, this has to have this sort of form, where H is a metric on, say, K inverse, which is just the holomorphic tangent space, right? Okay. So in other words, an ordinary kind of conformal metric on sigma itself. Okay. And in this case, there's kind of some very nice reduction. So it turns out that the holonomy, so you can kind of go through, once you have the metric, you find the Chern connection, you write down this holonomy. So you can find that kind of nabla itself kind of preserves a copy of SL2R inside of SL2C. Okay? So this is a rank 2 complex bundle. You would get kind of SL2R. The one thing that's a little bit tricky is that kind of the real structure here is not quite just kind of taking the bar. There's another, so the real structure on the Lie algebra would be something like this. So not just A goes to A bar, but you have to kind of conjugate by this little matrix. So this is kind of the price you pay to have kind of the other things be kind of in a nice form, is that the real structure has some slight variation to it. Okay, and so then we get kind of a map from sigma tilde into the symmetric space, and we're able to take the real symmetric space here. So this is going to be H2, this is also H2, and so this is going to be a harmonic map. So a row equivariant harmonic map. And in fact, and in order for this to be a harmonic map, this H is a hyperbolic metric. On the target. Okay? So it's not conformal with respect to the original domain, but once you kind of move to the target, this is another hyperbolic metric. Okay? So what Hitchin did is he noticed that this is a way of, this Higgs bundle setup gives us a way of parametrizing hyperbolic metrics on the quotients. So the Higgs bundle, and the only choice we made was this Q, which is the quadratic differential. This kind of parametrizes hyperbolic metrics on, say, n. I'm saying n instead of sigma because the conformal structure is varying. And so in fact, what you get is, so given a kind of a marked sigma, which I'll kind of think about as in the Teichmuller space of n, it's kind of like a base point. And kind of then the Higgs bundle theory, this the space of quadratic differentials over sigma parametrizes all of Teichmüller space. Okay. So given this base point, this is a way of parameterizing Teichmüller space. And it turns out this is going to be this Hitchin formulation. This is kind of the same as Mike Wolf's formulation, which was about at around the same time, but he kind of directly considered kind of harmonic maps from H2 to H2. Okay. But it's the same, it ends up being the same construction. Okay. All right. So this is kind of a way of, in nice cases, the Higgs bundle apparatus, I mean, we automatically get all of this, which is quite nice. And in particular, you can study these representations given by the holonomy of these flat connections. But sometimes there's kind of even more geometry. And so this is kind of one of these, a very nice way of thinking about this. Okay? And so this kind of makes sense because, I mean, and classically in Teichmüller space, so kind of a remark is that, so the space of holomorphic quadratic differentials is naturally the holomorphic cotangent space to the Teichmüller space at sigma. Okay, so this is kind of, it makes sense. I mean, there's a natural complex structure on Teichmüller space, and it turns out that quadratic differentials are more naturally from kind of most points of view cotangent space, not tangent space. But you can see that this is so it's kind of like it's to some extent it's kind of a version of an exponential map. You can kind of get all of Teichmüller space with this. And I wanted to kind of show you this in some part because, I mean, this is a situation where kind of where the stability condition is not is easy to check, right? And which is kind of nice. All right. Yeah, exactly. So yeah, when and kind of the Q equals 0 is, yes, exactly. Q equals 0 is the uniformizing hyperbolic metric. So in particular, if Q is equal to 0, then you just kind of, you recover the hyperbolic metric on the same Riemann surface, the conformal one. Whereas these other ones have, when Q is non-zero, you have different conformal structure. Okay. All right. Any more questions about this stuff? So let me try to at least talk about something that, I mean, this is not so new still, but maybe I'll keep this up just because, I mean, in case I need it later. And then I'll erase this. Okay, so another thing that I'd like to talk about is talk about this today and maybe a little bit tomorrow if necessary. So equivariant minimal surfaces classified via Higgs bundles. And so this is joint work with myself and Ian McIntosh, which was published in 2019. And so, so I have the following theorem. So let S be a closed oriented surface of genus G at least 2. Rho is going to be a so PU21, so this is a Lie group, which I'll explain. Rho is going to go from pi1 of S. So this one is going to be irreducible. And let F be a map from H2 to CH2. So CH2 is going to be the symmetric space for this Lie group, as we'll see. Be rho equivariant, minimal branched immersion. So we're going to assume F is neither holomorphic nor anti-holomorphic. So I mean, there's kind of a general fact. I mean, this has this is a complex manifold, so it's modeled on kind of the unit ball in C2, and it's also Kähler. So holomorphic submanifolds of Kähler manifolds are always minimal. So, but these are going to be kind of some special cases that that don't quite fit into this statement. Then the space of such rho comma F divided by, modded out by an action of PU21, this is equivalent to the following data. So sigma is going to be a Riemann surface structure in Teichmuller space of S. So D1 and D2 are going to be non-negative divisors on sigma. So these are just going to be collections of points, and the points are going to be weighted by positive integers. There's going to be a restriction on the degree. So with degree, S is just the surface, and this will have the complex. So yeah, so assume F is not holomorphic nor anti-holomorphic. So I've kind of hidden this. F goes from H2. So I'm kind of hiding this sort of. Yeah. Well, no, I mean, the thing is that H2 is going to be the universal cover of all of these Riemann surfaces in the Teichmuller space. So before we actually, so we're going to have a representation, so kind of a Fuchsian representation to determine what the point in Teichmuller space is. So the H2 is fine, it's just without the Fuchsian representation, we don't know what sigma is. But it always makes an S. Is that? Okay, so these are going to have, with degree, little d1 and little d2. Yeah, I just want the image is not a complex manifold. Yeah. Because I mean, these are, I mean, we'll see in these situations that kind of the Higgs field the Higgs bundle is going to kind of be degenerate in some ways in these cases. So with these have degrees d1 and d2, so this is just kind of the sum of the integers of these on these points, satisfying the following inequalities. 2d1 plus d2 is less than 6 times g minus 1, and d1 plus 2d2 is less than 6 times g minus 1. Okay? And so these inequalities, these are going to be the stability condition in this case. So it's kind of nice that kind of the stability condition is so clean. It only involves degrees and not kind of more complicated things. So, and this C, this is going to be a cohomology class in H1 kind of Dolbeau cohomology of sigma k minus 2 d1 plus d2. Okay. So this is going to allow kind of some little bit of extra structure at d1 and d2 pole structure. Okay. And k to the minus 2, this is going to be just the dual of k squared. Okay. So there are various invariants we can read off, which I'm not sure I'm going to have time to kind of talk about the invariants, but Maybe I'll just kind of leave this out. So there are various topological invariants you can get. Yeah. Yeah, so these have kind of various dimensions, right? So because I mean, this is something you can count the dimension of these things using Riemann-Roch, right? Yeah. Yeah, there are many possibilities for components, right? So it depends on the D1 and the D2, the D1 and the D2. Right? But otherwise, there's kind of no restriction on the divisors. I mean, there doesn't have to be any sort of special points like in algebraic curve theory. Yeah. Okay, so you can kind of, let me just say, I don't think I'm going to have time to explain what these are, so we can compute various invariants, kind of the Toledo invariant, and the Euler number of the normal bundle from the genus D1 and D2. Okay. So I'm not going to really have time to say what these are, but these are kind of various topological invariants. Okay. So that's not clear. Yeah. So that's kind of a. So the thing is, I mean, so the question is, you have kind of these representations, and I put in this extra bit of data for a minimal surface, right? So there are some situations in which kind of a given representation has a unique minimal surfaces. But these are quite special. So I mean, I guess if you start out with kind of with D1 and D2 are both empty, and the extension class, this is called an extension class here, is 0, then you get kind of a Lagrangian plane, so a totally real plane in CH2, which is kind of the most trivial case. So in that case, that one is unique, and if you perturb it a little bit in terms of the extension class moving away from 0 a little bit, that condition will remain, but it's there may be kind of once you get kind of farther away from this locus, then you may have run into some trouble.
Even one data, there may be more than one minimal surface.
Yes. I mean, this is even true in kind of a simpler case. If you do this in real hyperbolic space, right? So there are kind of some nicer situations called, I think, almost Fuchsian. Well, we'll see kind of an example that's like this, where the minimal surface exists and it's unique on the quotient by this representation. But in general, you just don't know. I mean, it's going to be. I think it is. I mean, it's expected to just be kind of rather messy, right? Yeah. So it's not clear if you get kind of all the representations here. And it's likely that you don't. And it's likely that for most representations, if there's one, then there's more than one, right? So it's all sorts of things. And this is known, this is definitely known in the case of hyperbolic 3 manifolds. If there's kind of one equivariant, so you look at kind of this, you take a hyperbolic 3 space, and then you kind of mod out by an action of the fundamental group of a surface, not of a 3 manifold, then you can kind of hope to get this sort of almost Fuchsian picture where you have kind of this nice setting. But I mean, there are other situations where you get, where it's known that you have kind of this sort of quotient manifold, but there's known to be multiple hyperbolic minimal surfaces with the same representation. And so certainly this is worse, I would say. So that's kind of a little bit simpler. Okay? All right. Okay, so let me So the projective model of CH2. So as again, this is kind of like so let E minus, this is going to be a, let's see, where did this go? Okay. So these are going to be all the vectors in C21 such which are time-like. Okay? Whereas this metric, so C21, the metric is the following, V of W, VW. So this is going to be V1, W1. So it's going to be a Hermitian and a product, but with this 2-1 signature. Right? Okay. So in this situation, so you can have, so if the V3 components are bigger than the V1 and the V2, then it is possible to have these light-like situations. And so basically, this is going to be a complex cone in C21. And then we can define CH2. This is going to be, you're going to project of E1. And so this is going to be inside of a C2 inside of a CP2. And so this is going to be the standard model. This is a unit ball in C2. Okay. All right. So so that's the projective model. So the group U21, this is going to be maps in GL3C, just 3 by 3 matrices, preserving this inner product. So it's kind of unitary with this group of this Hermitian form of mixed signature. Okay, and then PU21. So this is going to be, we're just going to kind of project away from this. Okay, so this kind of so this is going to be inside of say PGL3C. Okay. So that's what our Lie group is. I should say CH2 is a Kähler manifold. So, so I guess one way of kind of seeing this is, so CH2 is the quotient, PU21 quotient by the maximal compact, which I'm going to write it like this. So PU21, and then inside of U21, a maximal compact is going to be U2 cross U1. You can projectivize that. And sometimes people kind of projectivize this away automatically, but I think that's can be a little bit confusing in the notation, so I'm not going to try to do this. And so on the ball in C2, the metric is the Kähler form omega. So this is the symplectic form. So there's going to be I times del del bar log of 1 minus W norm squared. And so this norm is just going to be the ordinary norm, the Euclidean norm in C2. Okay. Some more facts about this is that kind of the sectional curvature of CH2 is always going to be between -4 and -1. So for every plane, for every point in CH2, if you look at a kind of a tangent space inside a plane, a two-plane inside the tangent space, its sectional curvature is going to be between -4 and -1. And then these So, and then there are going to be two types of totally geodesic subspaces, or I guess planes, two planes, and CH2. So one would be holomorphic. This would be sectional curvature -4. And the other is going to be Lagrangian, or you might say totally real. This would be sectional curvature -1. So these are kind of the boundary situations in terms of the planes like this. And then of course, there are also kind of non-trivial submanifolds. So there are also kind of Lagrangian submanifolds and holomorphic submanifolds whose tangent space at each point is Lagrangian or holomorphic. Okay. Let's see. So in this case, let me just write this down. So CH2 may be represented by Z1. I guess I've been using W's here. W1, W2, and C2 such that okay. So then a holomorphic plane would be essentially an example would be, say W2 is equal to 0, just kind of W1 plane. And a Lagrangian plane, for example, would be, say, so Wi is xi plus, oops, Wj is xj plus I. Yj would be, for example, say, x1 is equal to x2 is equal to 0. Okay. So these are kind of some two different setups here. Okay, so this is the geometry, a little bit about the geometry of CH2 and how you can kind of see this as a symmetric space and the natural metric that you get from the symmetric space. Another way of saying this, there's something called holomorphic sectional curvature, which is constant and negative in this case. Okay. So let's see. So there's other things to try to explain here. Let me. So I guess one thing is that so this is an extension class. So this classifies short exact sequences. Okay. Of the following form. Okay. So these are going to be, this is going to be the canonical bundle twisted by this minus D2. This is going to be anti-canonical bundle twisted by D1. This is a short exact sequence, and this will be a rank 2 bundle. And so the data that we're going to have here, and so let me try to make sure I put things in the right place here. So the data that we have here are, when we do this sort of extension, so let me, I'm just going to label this. So I just want to make sure I get the right one in the right place, which I may not be able to do. So. Okay, so maybe I'll just, okay, there it is. So this is going to be, so we want not only this vector bundle, but there are going to be these phi1 and phi2, and these are going to be two components of the Higgs field. Okay. So this is going to be a map from a line bundle to a rank 2 bundle. This is going to be kind of a projection from a rank 2 bundle to a different line bundle. Okay. Okay. Let's see. Very normal surface. What is the underlying bundle for the Higgs bundle? So the underlying bundle for the Higgs bundle will be equal to a this rank 2 bundle plus a line bundle. But since we're in a projective group, what we're going to do is force the line bundle to be trivial. That's going to simplify things. So, so in general, we're going to get this sort of structure kind of comes from U21 Higgs bundles, but when you projectivize, there's kind of enough freedom to kind of get rid of one line bundle worth. So we're going to change this to this. Okay. So this is going to be the Higgs bundle. All right. So, so there are other cases here. Let's see. So D1, this is going to be the set. Yeah, they're interchanging the two factors. So one is a map from one, I mean, tensor K, yeah. And then these are going to be some vanishing loci, so you have to kind of twist by these divisors. Okay, so D1 is the set of anti-complex points. In other words, so dF such that it takes T10 of H2 to T01 of CH2. So these both have complex structures, but this is not in general a holomorphic or, so an anti-complex point is where it looks at that point as if it's anti-holomorphic. Okay? But we're kind of ruling out the case. So these are going to be isolated points because we're ruling out the case where the entire thing is anti-holomorphic. And similarly, D2 is going to be the set of complex points.
So in the case of
Yep.
Equivariant map, the setup, it will be some kind of pullback of tangent bundle or something. And when you want to do a kind of differential of the map.
Yeah, it's something like that. There are going to be a lot of different bundles because, I mean, we kind of have to treat kind of the holomorphic and anti-holomorphic behavior separately. And so, so one of these, I mean, so D1 is going to be naturally associated with Phi1, D2 is going to be naturally associated with Phi2. Yeah. Okay.
Excuse me,
Yes.
just so that I understand. So as F varies, your D1 and D2 are varying, right? I mean,
The thing is, I mean, the theorem is that we will, from D1 and D2, then we will, so this is just kind of setup. So from the data, from these data points with these restrictions, we're going to produce rho and F.
F. Okay, got it. Okay.
But I mean, but we need to explain how they're related, right?
Right.
It depends on F. So it doesn't make sense to say.
Yeah, you don't.
Points are remaining fixed, moving on a good lot of points moving in a fixed sequence.
Okay, yeah, so, yeah. So let me, let's see. No, we're starting with these data. Start with sigma. You add in D1, D2 on sigma. You add in C, which depends on everything, right? Then you produce this. Yeah, you produce this. Yeah, so the main kind of content of the theorem is going from here to here. Yeah. Okay, So let's see. And then D1 intersect D2, this is going to be the branch points. So if a point is both complex and anti-complex, then it's a critical point. So then you, this is one of these non-emergent points. Okay? And so then the case that D1 and D2 are both empty, then the surface is Lagrangian, which so F, when you pull back the Kähler form, is identically 0. And so this is a theorem of Wolfson in the case where the, if you look at minimal surfaces in Kähler-Einstein four manifolds of negative Ricci in a compact case. Okay, so that is so that's kind of a lot of so are there any other? So there's kind of a lot of different things, and I've tried to explain kind of the ingredients here. So any other questions right now?
Instead of minimal then there always exists.
Yeah, for any representation, as long as it's not irreducible, yeah, any irreducible representation.
We can pull back the metric to get a conformal structure for which it is.
No, because I mean because the harmonic, the condition of the harmonic map depends on the conformal structure of the domain already. So if you kind of replace that with another conformal structure, it's no longer harmonic. Okay. All right. So let's kind of I have a little bit. Let's talk a little bit about the proof, I guess. So the proof uses Higgs bundles, and so I guess so GL3C Higgs bundles, we're going to have E of rank 3, and phi is going to be endomorphism of E, and so you want a metric M on E. So in the case that everything is stable, then you get is projectively flat. So in other words, the curvature is going to be a constant times the identity endomorphism, but the constant is not going to be 0 necessarily. Okay? So in this case, we're going to get a representation, rho, from pi1 of sigma to PGL3C. Okay? And this is going to be useful for us because, I mean, the group that we're interested in is PU21. This is the group of holomorphic isometries of CH2. And so it's naturally projective here, so we will kind of deal with this, okay? So we can kind of pass to U21, and in this case, the maximal compact is U2 cross U1, and we have kind of a Cartan decomposition. I mean, this has kind of or an analog of the Cartan decomposition. So we have kind of this Lie algebra plus the part P, which is kind of orthogonal with respect to the killing form. So P is going to be the following. So in particular, so what happens is, I mean, this is not, so I really want to kind of look at SU1 or something like this, but this construction still works. So when we're taking the quotient of the group by the maximal compact, then there's kind of a similar quotient of the Lie algebra. And what you wind up with is this kind of P, this orthogonal part. So this P is a model for the tangent spaces to the symmetric space. And so you can kind of see what so you can see this P has kind of, so these two blocks are kind of quotiented out, and you're left with this sort of thing, okay? And so kind of phi is going to be of this form. All right. So we're going to have E is going to be V plus L. So V is going to be rank 2. L is rank 1. So phi is going to be in so these two things are kind of the homomorphisms from the V part to the, so this is going to be like V times V, this is going to be L times L. Okay, so now what we're going to do is we're going to pass to the PU21. And so what we're going to do, we can kind of tensor with a line bundle. So the line bundle that we would like is L inverse. So when you tensor with a line bundle in this sort of setup, then this is going to change the curvature, but of this bundle, but it will still remain projectively flat. Okay? So we're going to use this. So in particular, we're going to replace V plus L with V plus I. So we're going to tensor the whole thing with L inverse. This turns to the trivial line bundle, and this is going to be the old V tensor L inverse. Okay? All right. So now what we're going to do is we're going to use the minimal surface equation to condition determines V. So we're going to have so the Hopf differential is going to be is up to a constant, as we saw before, trace of phi squared. And so it turns out that so we're going to write kind of phi as this phi1 part and the phi2 part, okay? So let's see, how much of this do I want to do? So the minimality condition so this implies that that either phi1 is identically 0, in which case, let's see. So F would be anti-holomorphic. Anti-holomorphic. Our phi2 is identically 0. F is holomorphic. So these are kind of, we're going to, I mean, these we kind of do this in the paper, but for the purpose of this talk, we're going to rule this out. Or that the composition phi2 composed with phi1 is identically 0. Okay? And so what happens here is that this so this is going to be like away from the zeros. So D1 and D2, which are going to be the complex and anti-complex points, away from the zeros of phi1 and phi2, we're going to have the following setup. So the fact that this composition is 0 means that this is a short exact sequence. And this is exactly kind of the collection of these short exact sequences, this is exactly corresponds to this extension class. So given, so in this case, D1 and D2 would be empty. With this extension class, you would have something like this. Okay. And so in this case, we can kind of think of, so phi1 is an element of, so it's going to take the trivial line bundle to V tensor K. So that's the same as kind of going from K inverse to V. And similarly, phi2, this is going to take V to the trivial line bundle tensor K, which is just K. Okay? So we produce this kind of extension class, and this gives us exactly what we need to produce both V and the Higgs field here. Okay? All right. So, and then I guess we can kind of, so these are going to be D1 and D2, these are going to be the 0 loci of phi1 and phi2. So, of the zeros of phi1 and phi2, we're going to have the following. You need to kind of twist these canonical bundles. Let's see. So K1 of K inverse D1, phi1, V, phi2, K of minus D2. So once we kind of twist by these 0 loci, then this means that these are non-degenerate maps at every point. Right? Okay. And so then we can use kind of, so then the extension classes exactly classify the set of V, phi1, and phi2. This situation. And then kind of the stability, which I may not have time to do, it kind of corresponds to these two conditions. And so you can work out kind of the notion of stability. It's kind of a little bit, you actually have to use this non-trivial rank, because the way we're setting this up, E doesn't have degree 0. So we're going to have to use this non-trivial rank to, so we're going to have to use the slope stability in order to do this. Okay. All right, so I think that's it for today. And so hopefully you have some idea about how this stuff works, but it's the kind of the sort of thing that you need to be able to kind of hammer down to till you find kind of, you can kind of get a theorem that's basically depends on kind of a Riemann surface and then at least kind of holomorphic type objects. So this cohomology class you can think of as Dolbeault cohomology, for example. Okay. All right.
Yeah. Any questions? Okay, so we thank this.
Okay, thanks.